got over 155 people who've registered, so quite a few of you guys there. We're muting everybody, but we are going to take questions, but not verbally. So via the chat within Teams, you can put your questions in at any time. My colleague Mike Kenny will get on and answer those as we go through at the end of the meeting. We may not get through them all, so don't worry, we will answer them separately via email or other medium. So we will get all of your questions answered, and don't worry that they may be silly questions. We're happy to help you with your flow chemistry questions there. Today we are Asynt, so we are a company that specialises in products for chemists, novel products, benchtop tools, and for some time now we've worked really closely with the University of Leeds, with Professor John Blacker and Nick Kapur, and they're going to be presenting the science and the chemistry behind fReactor today. But they're also very keen to work as collaboratively as possible with more academics and more industrial organisations. So if you like what you hear and would like to find out more about maybe potentially collaborating with Nick and John, then you'd be able to drop them a line at the later date. What I'm going to do, I'm not going to tell you any more about Nick and John. I'll let them introduce themselves and their department. We're going to start with Nick, and he'll be running you through the sort of the hardware side of fReactor, the physical properties of how it works, and then John will go on to more of the chemistry science afterwards. And then we'll take the questions via my colleague Mike. So with that, I'll hand over to Nick.
Thanks, Martin. Excellent. So thanks very much to Asynt for hosting this webinar. Myself and John will introduce ourselves in a moment, but before we go into PowerPoint, I just thought I'd show you what a typical fReactor is. So this is a single stage of 5 that normally sit together. It's very easy to use. Okay, and I just want to show you how easy it is to use before we go into the video. So there's a thumb screw on the front. If you take that off, you can get into the inside of the fReactor. So there's a glass window, and then there's a little magnetic stirrer. And reassembly is just the opposite process. So if you need to get in and clean these things out, or after you've finished your reaction, you can do that. And just reverse that. So very, very quick and easy to assemble and disassemble. They're rated to tens of bars of pressure. I think we say about 7 bar is safe, but obviously there's an upper limit above that. And it's got ports on the side of this. So this is just set up with 1 input and 1 output. And there are 2 stopper ports in here. But again, it's very easy just to take these out. There's another pipe there. So that's now got 2 inputs and 1 output, or 1 output. And then you can put instrumentation in. So if I take this port out, this is just a thermocouple, standard thermocouple going through a standard HPLC fitting, and that can screw in the side so you can measure temperature. So that's the single units that we'll be talking about, and I'll show you how those fit together. So I'll show you that now before I go into my PowerPoint. So let me just share my screen. So as Martin said, we're talking about flow chemistry in general today and talking about what we've been doing with the fReactors. So I'm Professor Nick Kapur. There we go. I hold a chair in applied fluid mechanics and a degree in chemical engineering. I'm based in the School of Mechanical Engineering at the University of Leeds. And my interest really is in the fundamentals of fluid flow in many different situations. And I work very closely with industry as well as many other groups in academia and realizing flow concepts. And I've been particularly working with John and with an IPRD for about 5 years now, where we've been designing different types of flow reactors to enable different types of chemistries. John, do you want to introduce yourself briefly?
So, hello everyone, I'm John Blacker. I'm Professor in Process Chemistry, University of Leeds, Director of the Institute of Process Research and Development, which is dedicated to developing new research and development methods in process development and manufacturing. And my particular expertise is around route design and chemical process research and development, including a lot of flow chemistry, as we're going to talk about today. So,
thanks, John.
Nick.
So John mentioned IPRD. So IPRD is our Institute of Process Research and Development. And it's within IPRD that we've done many of the developments of the fReactor. This was never a big funded project externally. It was something that we started. And the students within IPRD, they're a mixture of engineers and chemists and biology students, and the academics have all got involved in this project. And it's really, IPRD is, has a physical base. It's got really great laboratory facilities for doing small scale through to large scale synthesis of chemicals. And around that is a whole group of academics working in different areas. So it's a really great place for students to work and postdocs to work and for research to happen, because there's this very interdisciplinary research environment. So that's sort of where they've come from within the University of Leeds. So what I'm going to try and get over to you today is what we've been doing a little bit around flow chemistry and more about the fReactors themselves. So the single fReactor unit that I showed you is a single continuous stir tank reactor. And you can see two of these down at the bottom of the screen. So this is our standard size fReactor. It's got a volume of about 1.8 milliliters, and this has a volume roughly of about 8 milliliters. So this is a bigger scale unit that we're just launching, and they sit on a stir or hot plate. We've celebrated this one with balloons, and you can flow in and around those, and I'll be showing you that in a moment. What I want to get over to you today in my part of the talk is how and why we use them, and some examples of chemistry, and John will be talking quite a lot about different examples of chemistry. So I thought I'd start with a video, and this is a video of reactors in operation, and what we have within this is it's a physical process really. So we're mixing oil together with water and a green dye that we've put in the water phase, and you can see just how easy and straightforward these are to use. So this is the fReactor unit on the hot plate. So there's 5 of these together, and I'll mention why in a moment. And we've got a dual feed into the first fReactor. So that's our first fReactor. And you can see here in this syringe, we've got our lovely green water, and in the bottom syringe, we've got our oil. And these are sat on a dual syringe pump. So that's a pump that pushes the syringes in at the same rate. So we've got a 1-to-1 ratio. And there's a stirrer hot plate within this, and that's going to provide the stirring action. So there's a magnetic stirrer in each of these. And you can see fluids coming in over on the left-hand side, and it's flowing its way around through these 5 stages. And you can see, if I just pause that there, you might be able to see if you contrast good enough, you've got this very fine emulsion of material leaving after the last stage. Okay, so that's a very typical physical operation. There's no real chemistry taking place, but it gives you a feel for what's going on. Now, this is a slowed down video of actually what those stirrers are doing. They're actually bouncing around within the reactors and giving really good mixing. Now, I just want to contrast that with the other type of reactor that people often use for flow chemistry, and that's a tubular reactor. And what you'll do is you take a tube and a T-piece, and as you'll see, you bring oil and water together. So there's our water phase and there's our oil phase, and that mixes within the T-piece and then flows out. Now, although it looks really pretty, you've got this very, very regular drops of water within the oil phase. So we've got an oil continuous phase. You've actually got very small amounts of surface area for any mass transfer between those 2 phases. So the mixing in this type of systems nothing like the mixing that we see within the fReactor system. So this is an example of a multiphasic type reaction. So that's quite quick, but you'll see I've broken out some of the slides in a moment. So just from a physical perspective, what we have on the left-hand side here is our dual syringe pump. So you have a choice of how you want to pump, and the way we've tried to design the fReactor is to make it as flexible for people as it can be, okay, without becoming too difficult. So to use a fReactor unit, this is the fReactor shown in the dotted circle, you attach a pump. So we're using a dual syringe pump. We often use single syringe pumps, and then you can control the ratio of the flows independently. Syringe pumps actually are very convenient, particularly if you've just got, say, an aqueous phase and an organic phase. You can also suspend solids in them, but you have to make sure that you don't separate your solids out in your syringe. So sometimes we sneak an extra stir a hot plate under here, and we put a magnetic flea in there. So there's tricks like that you can play. You can use peristaltic pumps, but the pressures you might achieve might not be quite as high as within a syringe pump. Sometimes you use HPLC pumps, gear pumps, and diaphragm pumps. So there's a kind of a choice really around pumping, but actually syringe pumps with an appropriately selected syringe, so the materials have to be compatible with what you're using, actually are very convenient as a starting point, and that's often where we start. So things that you might consider when you're choosing your pump are the maximum pressure you want to generate, whether you've got solids in there, material compatibility, and then general flexibility. And really that's it. So you take your pump, you stir a hot plate, and many of us have stir hot plates in our labs already, and you add on a fReactor kit. And with a bit of chemistry, you become a flow chemist. It's nothing more complicated than that. And I think sometimes we build these things up in our minds, and actually it's really easy technology to access. Now, when we're operating flow chemistry equipment, we tend to go through different phases of the process. So the first phase is a startup phase. So typically, and in this example, I've started with the oil phase within the fReactors. So I would have turned this on, I would have flown oil through the reactors at a few milliliters per minute until I've pushed all of the air out of the system. Okay, and then I'm going to go into my, well, in this case, a physical transformation phase. So I would turn on my aqueous pump and I would turn on my oil pump, and you can see it takes a few minutes for our material to flow from the inlet to the outlet. So you can see, I think, probably just in these two reactors, it's starting to turn green, whereas these are still clear. So we have this startup phase where our materials are coming together for the first time. And if we were monitoring something like yield, what we would see is over time, our yield of our product would go up, and then it reaches a steady state phase. And we can run this for as long as we want. And that's one of the really nice things about flow chemistry is if you need more material, you leave your reactors running for a longer time, and you can generate material and scale up data in that phase. Okay, and then we have the shutdown phase. So maybe we turn off one of the two feeds and then our yield would start to drop. Or we could just turn off the reactor at that point and maybe empty the contents out. And typically, around 2 to 3 volumes of the whole reactor is the amount of material we have to flow through to reach that steady state phase. So roughly, this is about 10 milliliters of volume within this reactor. So typically 20 to 30 milliliters of flow goes through the reactor before we reach that steady state phase. Okay, so that's typically what we see within a flow chemistry situation, as opposed to a batch chemistry situation where we might bring our materials together and we don't change, we don't continue to add. In some cases you can do, but generally we bring our materials together at the start of the reaction, we stir them, and they change continuously with time until the end of the reaction is reached. So that's one of the differences between flow and batch chemistry. Now, within our reactors, and one of the reasons we designed reactors was because we were particularly interested in multiphasic chemistry. And John will give you some of the reasons about why we're interested in multiphasic chemistry. But what we have within each reactor is we have an active mixing. So there's a mixer that bounces around within the fReactor, okay, and produces really good mixing between different phases of materials. So in our case, we've got two immiscible fluids, and this active movement maintains a high area of liquid-liquid interface. So if we're expecting chemicals to transport from one phase to another, maybe after a reaction or during a reaction, this is a really great way of maintaining this interface. We can suspend solids, so we can suspend catalysts, and we can actually crystallize within the reactors as well. And because we're continually moving material around, we find that the crystals tend to stay in or suspended in the solution. They do sometimes aggregate on the walls of the reactor, but generally not so badly. And actually, we've performed some really nice crystallizations within these. Now, ultimately, you might get a blockage, but then you've seen how easy it is to shut the reactors down to clean things out. And we've also done quite a lot of gas liquid mixing as well within the systems. And I'll give you some examples in a moment. Point the back on. So I suppose really the difference between the reactors is that we've got active mixing within each element, and there's a really good local energy input. We're adding energy into our system to keep those two phases mixed together, and that means we've got really good mass transfer between the two phases. Now, just by way of example then, I'll jump over to the right-hand side. This is a typical tubular reactor system. So this pipe might be wrapped around a mandrel that keeps it hot. We'd have much poor mass transfer really for these multiphasic systems. So you can see the interfaces between the green and the clear actually are not big areas per volume of fluid. Okay, so that means we've got diffusion control of these interfaces, and even with single phase chemistry, so maybe we have two miscible chemistries coming in over on the left hand side, then it's still diffusion controlled. Okay, so again, the mixing characteristics are very slow within these types of systems. So over on the left hand side then, reactors, just by way of an example then, so if we're running at 2 milliliters per minute, typical mid-range flow that we would be using for these, it gives us about a 4-minute residence time within the reactor classic. So that's how long it takes from, on average, from the inlet to the outlet. That's what we mean by residence time. And if we were doing that within a tubular reactor system, we would be using about 5 meters of an 1/8-inch diameter PFA tubing, and we would need a heating element around that as well. Okay. Here again, right. So I just wanted to talk about the operating characteristics of the reactor and what these have really allowed us to unlock within IPRD. And what we're finding is that actually having these within the lab, people go to them without much prompting, they pick them up and they start to use them. They're very easy to use, okay? I mean, I showed you, if you can finger tight a fitting, then you can assemble a reactor, and it's really that easy. So there's a very low barrier of entry to flow chemistry, but it's a very effective flow platform from a chemistry perspective. It's reusable and robust. I think say that there's a pressure limit of 100 psi, so a 7-bar pressure limit on those. So why that's important is because we know that to push our reaction rates, we generally want to go hotter with our reactions. And many of our solvents will boil before the temperatures we ideally want to reach. So by putting a back pressure regulator on the end, what you're doing is you're increasing the pressure within the system, and the boiling point of your solvents also goes up. So it allows you to access higher temperatures and faster rates. Okay, so that's why we tend to use back pressure regulators. And if we've got gases in there, so if we're doing gas-liquid reactions, then by pressurizing the gas, we end up with a sort of a higher partial pressure. And that means there's a faster mass transfer from our gas phase into our liquid phase. So that's something about pressure. The materials of construction, if you need specific materials, you can talk to Asynt, but the kind of base unit is a peak reactor, so it's very robust to most chemistries. I think it doesn't like chlorines and bromines and things, but for most chemistries, it's very good. It's got a temperature rating, usable rating of about 140 degrees C, and then it just depends on the pipes and other bits and pieces that you're using. And you can use that with the standard hot plate, and it's easy, and you probably have one. So there's also been quite a lot of chemical engineering thought that goes into this. So you can see straight away we've got roughly exactly 5 and roughly 2 milliliters per reactor. So about 10 milliliters of volume. So doing this in 5 2 milliliter packets is better than doing it in 1 10 milliliter packets, okay, because of the residence time distribution. So we often talk about a mean residence time, but some fluid entering a reactor like this can go through very quickly, and some fluid can hang around, and that's what we mean by residence time. So some packets that go in spend a long time in there, some packets that go in spend less time in there. And the wider that residence time is a sort of means that you've got more variation within your reactor. And chemical engineering principles say if we've got smaller reactors and more of them, that's better than a larger reactor and a single one of them. And I'll talk about these links in a moment. And we find there's great flexibility within these reactors. I showed you how easy it is to add pipes in. Sometimes we feed into our first reactors only, sometimes we put other feeds in down the cascade, maybe to try and keep a particular reactant at high concentration. All of that's very flexible within our reactor system. Fine. So one of the things that we've been trying to do with Asynt is we try and feed technology through so that as we develop pieces of kit within our laboratory, these become available through Asynt. You know, there's a product development cycle that we go through, and ultimately it gives you the same robust platforms to work on that we're working on, and with really good engineering principles. As you can see, they're really easy to use. So this is an example of a gas liquid reaction using some photochemistry. So this is tetralin to tetralone. So there's air in the system, so that's our carrying oxygen, and then there's a photochemical initiator within our system as well. Okay, so we developed a cascade of UV 365 LEDs within our labs, and you can see they're not, you know, that's not commercially viable yet. It's still quite laboratory based. Lots of advantages within CSTRs with photochemistry, because actually you've got this really active mixing, and you can maybe see that on the next slide. Because you've got active mixing, it's mixing light, mixing fluids up into the active region where the photon count's really high, and then back down again. And that's contrasted with photochemistry within the tubular system. So if you were doing a gas liquid reaction like we're doing here, and this is an example of what would happen, you would have slugs of gas, slugs of liquid, slugs of gas, and then your light intensity will be highest nearest the top of the tube. So there's really good advantages to doing photochemistry within CSTR systems, okay? And we found really good performance of our gas liquid systems in this example here. And if you need further information about these, feel free to contact us afterwards. And this is where we kind of at the moment. So we're working really closely with Asynt to bring photochemistry modules out. So these are our, I don't look beautiful yet, but they're performing really well. They've got 365 LEDs in them, and they sit on our standard reactor plates. So this kind of idea of modularity and allowing you access to broader chemistries, and also allowing you to choose what you want to do your chemistries is a really nice concept that we're developing. I just wanted to show you two other things as well, really. So this was an example of a hydrogenation reaction, and we weren't actually using the fReactor for flow reactors, we were using them as batch reactors, okay? And the idea behind this was, because all of these fittings are really standard, you can kind of go to catalogs and choose what you want to buy. So here we've got a back pressure regulator, and this is a safety regulator within this system. Here we've got 2 ports blocked up. And here we've got a little valve that's a little bit like the valve on your bicycle. So you put this in to the fReactor, and what happens is you can pressurize with your syringe, and it pushes gas through the system, and then it's locked into that reactor. And by doing this multiple times, just like when you pump up a bicycle tire, you can essentially pump up your reactor to a particular pressure. And it's very easy to generate tens of bars of pressure using a system exactly like this. Okay. The nice thing about the fReactor system is you get 5 of these, so it's very easy to heat and run 5 screening reactions at once. And I think John might mention something about those. We also did some work where we were measuring the pressures within the reactors. So this is a standard pressure probe and an adapter, and there would be a pipe that went from there into our reactor. And from that, we were able to get some mass transfer characteristics. And actually, we found, so this R number is the ratio of liquid, of gas to liquid. So we found for a particular R number and a particular rotational speed, we got really good mass transfer characteristics within our systems, okay? And shown over on the right-hand side is a PAR reactor that we have in our lab. I think it's a 2-litre PAR reactor, overhead stirred, much more traditional, larger volume reactor we would have used for hydrogenations. And you can see we're actually getting much better mass transfer characteristics than we would in the PAR reactor, but certainly of the same sort of size. So it's showing that you could use these for screening, for example. So you can pick off a reactor after 10 minutes, 20 minutes, 30 minutes, quench the reaction and see where you're at. And then this is just one last slide, really. This is a standard pH probe. We've also just worked with Asynt just to launch a new lid for the fReactor where you can take one of your standard 12mm probes. So it could be conductivity, it could be pH, whatever you want it to be. And that fits on in place of our normal lid onto the fReactor, and you can measure other things. I showed you an example with temperature, but now you could add pH, for instance. And like I said, we're developing new technologies all of the time, and we're always interested in passing these through. But in the interest of time, I'm not going to go through all of those. Last thing I just want to say is, myself and John are really passionate about getting people to use flow chemistry. It's one of the, the pillars of green chemistry, and we think it's really important. We have developed some educational content as well, because we realize people haven't necessarily done flow chemistry as undergraduates, as chemists. We're trying to change that within Leeds. Our undergraduates, when our labs are opening, do flow chemistry with John. But we've put some information on these web pages so you can find out about flow. There are some online modelers in there, so you can explore what happens if you have 3 reactors compared to 5, and what that means for residence time, and some of the technical language that I've used today that you might not be that familiar with. You'll find lots of information on those web pages. Okay, and I think that's about me done. So I'm going to stop sharing my screen and hand over to you, John, who's going to talk about chemistry.
Right, so following on from Nick then, I guess the first thing to say is, why do we want to do multi-phase continuous flow chemistry? And the reason is that when we're doing process development, most production processes, most processes involve gases, liquids, solids, and various combinations. And if you're using tubular reactors, there are definitely limits on having gases and solids in there. They work very well with liquids. And the reason is that we often exceed material solubilities in order to try and improve productivity. So we might feed in solids, or we might get solids produced within reactions, or we might generate crystals as we're going through. We might have solid catalysts and so on. Processes can often require or evolve a gas, and so again we can end up with multi-phase systems. We might want to do liquid-liquid reactions with 2 liquids in there, for example, during workup and extraction, things like that. Or we might want to do crystallization, where we generate crystals in flow as well. And as we're all taught as undergraduates, batch reactors work very well with that, because the flea, the round bottom, in a round bottom flask with magnetic stirrer, they cope very well with lots of different phases. And we never even think about the mixing really in there as chemists. And when we try to do reactions in tubular reactors, as people know, they perform very poorly with solids, and gases and liquids are even problematic as well, though there are ways around that, some of those. And what chemists tend to do is they tend to circumvent or avoid the problem by designing homogeneous liquid systems. So they dilute things down until everything's soluble, and then they can flow it through a tube. But the consequence of that is that you've got a system that's less productive. It limits the scope of the reaction because you might have things that are still not soluble when you dilute them down, and it can ignore separation and workup aspects as well. So that's why we wanted to work on multiphasic flow systems. And the fReactors was one way of doing that, as you've seen from Nick's presentation. So I'm going to tell you about some examples of the use of the fReactors. So I've got 6 examples here. First one, an undergraduate experiment that's very instructive and very easy to run. Second one is a bit more complicated. That's either a gas liquid solid system as a palladium carbon hydrogenation, or as a homogeneous catalyst, ruthenium binap as gas liquid system. I'm going to talk then about biotransformation using oxygen together with the water in which the enzymes dissolved. Then a 2-phase system using bleach and toluene to do an N-chlorination. Then a crystallization, or 2 different types of crystallization. And lastly, a more complex example, which is an extraction, a liquid-liquid extraction. So to start with then, the undergraduate experiment that we've run for several years now, and is actually published in this paper if you want to get more details from it, involves the selective reaction of a diamine, a difunctional substrate, with acetic anhydride, and the diamines dissolved in water, and the acetic anhydride is dissolved in toluene. And when the two are mixed together, you get a 2-phase system. And then the better the mixing is, the better the rates of reaction. But then there's a few more complicating factors here, that when the reaction to form the monoacetylated product occurs, the side product is acetic acid, and acetic acid can then protonate either the starting material or the monoacetylated product, and then change its phase behavior, so it goes from the organic into the aqueous phase. If there's overreaction, it can diacetylate the product, or if there's underreaction, you get starting material that remains underreacted. So there's quite a lot of physicochemical principles that are introduced in this, and we get the students to start with a batch reaction and generate the data there. So you can see in these tables, they're getting 63% conversion and only 54% selectivity for the monoacetylated product. And then we get them to test a tubular reactor, so the 2 syringe pumps, a T-mixer, and then just try to do the mixing within the tube. And they get a slightly better conversion, slightly better selectivity, but it's still not as good as we get in the fReactors. So then they get the fReactors where there's active mixing this time, and this time the conversion's higher, and the selectivity for the monoacetylated products much longer as well. And what the students can do, they can change the variables. So they can change the residence time, they can change the ratio of the acetic anhydride or the diamine, they can change the temperature, they can change the pH, the solvents. And so you can imagine there's lots of variables which they can test and see what the effect on the selectivity in the reaction is. So it's a really good example to be able to introduce, all the things it can do. And one thing that amazes them is how many experiments they can do in a day. So when they reach steady state, after, as Nick said, 2 or 3 reactor volumes, so maybe 10 mils in this reactor here, they collect maybe 2 more reactor volumes, and then we can analyze the product by NMR, and then they can see very quickly the change in the variables and what effect that has on the selectivity in the reaction. So it's been a really successful experiment, and the details, as I say, are described in this J Flowchem paper, but also in the OPRD paper here. A second example is a gas liquid solid system. So this is a typical reaction where we want to hydrogenate nitrobenzene, so not a very interesting substrate, but nevertheless, you know, a typical reaction. So the way in which we do this is by slurrying up the palladium carbon in the methanol solvent here, and that's in a syringe, and we have a flea introduced inside the syringe with a hot plate underneath it that maintains the palladium carbon in slurry. And then as we pump the palladium carbon into the reactor, it maintains it in slurry. And then we inject through syringes hydrogen at multiple points through the reactor. So in that way, we can use the continuous flow system here by injecting hydrogen all the way through. And then as it flows through, then the product comes out. And we can use a back pressure regulator to generate pressure within the system. So in this case, it was 9 bar pressure. We ran it at 25 degrees C and we had a residence time of 10 minutes. But how did we know to use those conditions? Well, what we did first of all was to actually run the reactions in batch. So we had 5 separate batch reactions, each with the palladium carbon slurried inside them. And then we pressurized them, but ran them for different times. So in reactor 1, we ran it for 5 minutes, reactor 2, 10 minutes, reactor 3, 15 minutes. And then all we did was take it off, open up the reactors, and then analyze the conversion with time. And so that gave us a kinetic profile that allowed us to determine what was the starting point for the residence time in the reactor. So the system was made easier by the ability to just syringe in the hydrogen directly, and it avoids the usual thing of using balloons that people do. And you saw Nick's picture earlier with the balloons on, that's what the balloons were, hydrogen. So transferring the system to continuous flow was very easy to do. And then we could start to develop the system temperatures, ratios. We actually looked at compartmentalization of the palladium carbon in each reactor by putting a little frit in there and stopping the palladium carbon flowing from one reactor to another, using this internal frit to actually maintain it within each reactor and flowing the liquid across. So a gas liquid system we tested was this one here with a dihydro amino acid using ruthenium binap as a catalyst. And this is a soluble catalyst this time. And again, we determined the conditions in the batch and then translated this into flow, this time with a residence time of 30 minutes and 9 bar pressure, slightly exceeding the safety limits, but anyway, it's still fine. The safety limit's actually 40 bar pressure, and that's what it's been tested to. So I don't recommend you go to 40 bar, in which case these fittings blew out. But if you keep round 7 bar, 9 bar, you should be absolutely fine. And in this case, we achieved high conversion